Good evening, everybody. Welcome to a special series of the Ehrenfestii Colloquium, which is promoted by the Delta Institute of Theoretical Physics and brings us our community, a wide, as you can see, many faces of our colleagues from Utrecht and Amsterdam, as well as Leiden. And so this is a special series of events that brings here eminent theoretical physicists worldwide. And so the honor of the introduction tonight will be given to one of our colleagues from Amsterdam, Jean-Sébastien Caux. Jean-Sébastien, please.
So I guess this is really breaking with the Ehrenfest tradition to have an Amsterdammer do the introduction for the speaker for tonight. I knew that I would get flack from you, but it's okay. It was all rearranged with the actual organizers of this. I mean, it's a great honor for me to introduce somebody to you who you probably already know. It's the feeling I had the first time I met him, which happens to be just a few months ago. We met in France at a conference, and for me, I've been working for so many years with his papers, with his books, with everything he's written, that I almost felt that I knew already who he was as a person. I felt almost that I had been supervised by this person. So actually, the first time that we met, it's a nice little story, because I was talking about these correlation functions in quantum spin chains, and then you see particular shapes in the correlations that correspond to dispersion relations and excitations that are called spin-ons. And then essentially, in the audience, of course, was the father of the concept of spin-ons, looking at my graphs, and at one point he protested and he said, "You keep mentioning spin-ons, but you do not mention my name." I had to provide an explanation, which was essentially that everybody knew him, so there was no need. But tonight maybe I can make amends a little bit and tell you a little bit more about Professor Faddeev. I'm sure that you're well aware that he's somebody quite special in our community. In Amsterdam, just a few days ago, we had a mathematical physics colloquium with 2 talks. The first talk actually had as a title the bridge between mathematics and physics. And the second talk, like I said then, was actually presented by an actual bridge between mathematics and physics, impersonated by Professor Faddeev. So he's, of course, become very famous very early on in his career for his solution of the 3-body problem. As a theoretical physicist, of course, he can, as a human being, actually, he can lay claim to be the only one to have actually captured ghosts in his career. But for me, essentially, the most important contribution that he's delivered is, of course, his creation of the modern formalism, the modern way of thinking about integrable models in the shape of the, we would call the Algebraic Bethe Ansatz, these days, quantum inverse scattering method. I think this shows you really the quality of a scientist and of a kind of educator that he is, because if you look at the school, the Leningrad school of this time, so from the late 70s to in the early 80s, you really see the names of the students that he produced at that point. These people are all towering figures in the field today, and I think they would all recognize that the origin of their love for the subject and their devotion to its contents really comes from the environment that Professor Faddeev produced at that time. So, I mean, of course, the success that he's had in the scientific literature with all his results is clear for us all. But for other people, who don't really know how to evaluate scientific quality, then you can measure that with prizes. So I've had many good discussions with Professor Faddeev about the current sickness of the scientific community to measure everything in terms of numbers, impact factors, citation statistics, and things like that. So in honor of Professor Faddeev, I propose to introduce a new positive integer index to qualify the quality of scientists, and that is the number of medals you have won. Right? So actually, if you look a little bit at the number of medals that he has won, well, maybe we should just extend it to the prize. Then actually the list becomes almost laughably long, because it includes, Danny Hanneman Prize, Dirac Prize, Max Planck Medal, Henri Poincaré Prize, Shaw Prize, Lomonosov Gold Medal, etc., etc. But also, he received something which none of you will ever even be able to dream having, And that's essentially the order of Lenin. The particular reason why this was given to him at the time when he got it is something for private discussions. I've learned that directly from him, and I will not share this with you. So, without further ado, I will just leave the floor to him, and wish him the best of luck in front of the Leiden audience.
We zetten op z'n bank.
Just switch.
Does it work? Yeah. Mm-hmm. Okay. Yeah, it works. Very good. So thank you very much, Jean-Sébastien. It's really a pleasure to be here. I must say that it's the second time I'm on Ehrenfest Colloquium, because I was here, I don't remember exactly when, in the beginning of 90s, I think. I was Kramer's professor in Utrecht, wonderful leg of your triangle, yes. Delta is 3 points, yeah? And so I came here also. Maybe I also already spoke about this integrability, but on more concrete way. Today I will give you very general lecture on this development of this notion, and so advertise it somehow, because okay, still works, yeah. So I recently mentioned that if you look at HepTH in the beginning of this century, you will see word integrability more often than word string. So, which of course is different from 90s. Yeah. Anyhow, so what I will want to speak about, you think is?
Let's find the optimal compromise.
Mm-hmm. So let me begin. So I think integrability, or complete integrability more exactly, is a notion from 19th century. It's associated with the names of Jacobi, Liouville, Hamilton, and many other famous mechanicists. And it's connected with some special property of the ordinary differential equations in Hamiltonian mechanics. Namely, so usually in Hamiltonian mechanics, we begin with phase space with coordinates, call them psi. Which one? Up. Oh, I don't see which is the color.
This one.
Here. But it doesn't. It's very weak. No, it's call them psi. Yes, and there is a property which is called Poisson bracket, which is written in terms of the antisymmetric tensor, contravariant tensor, two tensor, which satisfies some special differential relation, which says that this bracket has satisfied Jacobi identity. So it's antisymmetric, and there is some differential property which you all know. And then, given this structure on the phase space, you can also introduce Poisson bracket for any functions on the phase space. And as we know, functions are just observables of your mechanical system. Then in terms of this bracket, the equation of motion, time dependence of variables is given in terms of this equation. And then we can say that among the variables which turn in time, maybe some of them which doesn't depend on time. Those are called conservation laws. And there are some conservation laws in general, but we say that complete integrable system is that in which besides H, there are at least n-1 integrals of motion in involution. I'm a little bit wrong here. It's in the case when omega is not degenerate. So omega has inverse matrix. Otherwise, there could be some trivial integral of motions which have nothing to do with dynamics. So they compute with Hamiltonian and that compute among themselves. Then there is a theorem, is that as soon as you have integrals of motion, you can take half of them as kind of coordinates and half of them as conjugate momenta. So you can change, find the change of variables such that there are variables A, which are commuting, theta, which are commute, and theta and I are commuting by Kronecker function. Which means that, of course, that I's are conserved and thetas are changed in time linearly. It's linear equation without time here, so solution is initial value plus this phase times time. So in the first examples, this theta had values on the torus, and so they are called angles. And conjugate variables are called action. So finding angle action variable became a kind of sport in mechanics in the end of 19th century. And the most famous solution is that of Sofia Kovalevskaya, some special top, which was not clear that was it completely integral or not, but she found these conservation laws. Well, but on the other hand, of course, this was kind of exotic question in mechanics. Maybe there were some applications, but not so much. And I think that to the middle of 20th century, the mentioning of complete integrability was kind of in this devoted chapter somewhere in mechanics textbook and so on. But then something happened. Namely, I cannot explain how, but because I also learned about it later than it was invented. So some particular equation of hydrodynamics with the name of Korteweg de Vries, so these famous Dutch people. It describes water in the shallow down. And so this equation is just Euler equation. But then this term which describes interaction of water with the how you say it? Don't know. Yeah. Yeah. So in particular, if you consider case when we have the space just full line and consider that the V goes to 0, or excuse me, V goes, what's that? V goes to 0 when x goes to infinity, then the space of all such functions is Poissonian. You can introduce Poisson bracket that V of x and V of y is delta prime of derivative of delta function. So x is kind of number of your variables. It's of course infinite number of variables, and so matrix omega is constant because it's somehow x and y are just labels, and so it's kind of constant. It's antisymmetric, but it's a little bit degenerate, so that integral of V over all space is computed with everything. But modulo this particular integral, which is trivial or not interesting, is now non-degenerate, and you can speak even about angle action variables, and in one way or another, or about canonical variables, you can introduce them easily. So I want to tell you that in textbooks, when you learn quantum mechanics, classical mechanics, from time to time you always begin with P and Q, canonical variables. Now I claim that it's not necessary. It's enough to have some variables on the full phase space. And now this delta prime of x minus 1 can be shown to be canonical, but then you have to take Fourier transform of imaginary part, or real, or even part, or odd part, and so on. But it's somehow full phase space, which Americans didn't understand, so they begin to introduce momenta conjugate to V, and then constraints and so on, but it's not necessary. So then this is Poisson bracket and this is Hamiltonian, usual square of derivative, which is kind of good, and then this V cube, nonlinear case. And then this equation have a very interesting solution, which is somehow behaves as a wave with maximum at x equals 0 and then going down very rapidly to infinity. So this solution, and maybe combination of such solutions, were dubbed by these people as solitons. Apparently they thought that there will be application to particle theory, because in particle theory you speak about hadrons and so on, electrons and photons and so on. So they call it soliton out of solitary wave. Recently, going along beach in the vicinity of my house, I found, I think, very beautiful picture of solitons. You see there separated waves. These are cos squared, cos squared, cos squared, and there is nothing in between, so it's really a nice picture of solitons. I'm very proud of it. So, what happened in the paper of these four authors was that they have found, in a way, explicit solution of Korteweg-de Vries equation. Namely, but for that they used very strange tool. They used quantum mechanical scattering problem. So it's completely classical equation of hydrodynamics, but in solving it, you need auxiliary quantum mechanical problem. Quantum mechanical problem is just that Schrödinger equation on the full axis, where V plays a role of potential in the scattering. So as we know from quantum mechanics, this equation have the scattering solution. If you have incoming wave from minus infinity, it goes further with some transition and then reflects in opposite direction. So there are this transmission and reflection coefficients. There is unitarity, sum of square equal to 1. And what's interesting is that out of the scattering data, essentially, and also some characteristic of discrete spectrum, if we have negative part, then there is also discrete spectrum in this equation. Out of this data, one can reconstruct potential. Moreover, so there is kind of one-to-one correspondence between, once more, so this thing. Yeah. Between V and R. Well, also R and something else. But then it turns, what they had found, I don't know how, but they did, that if V changes now with time by means of Korteweg-de Vries equation, this dynamical model, then R changes with time very easily. It's multiplied, it's just multiplied by factor I, e to the I, k cube t. So logarithm of R is changing exactly like angle variable. It has its initial value and then linear in time increase. I learned about this in strange time. So 4 years after it was invented, I was in a conference on inverse scattering problem. That's a completely different mathematical domain in which I worked a lot. And then I have heard a talk by Zakharov and Shabbat, who were in Novosibirsk, and they described the second equation for which this trick works, namely nonlinear Schrödinger equation. So I came, Zakharov was kind of colleague of me, we come evening, begin drink a little bit, and then I say, but look, logarithm of R is linear in time and modulus of R is constant. This is angle action variables. He said, well, yes, maybe yes. So, and we separated, and it was February maybe. In March, I was working at home because I knew a lot about the scattering problem and found exactly what we need. So what you need, you have this delta prime Poisson bracket, and you have to recalculate it in terms of scattering data. And this can be done. For that, you have to know a lot of tricks with just with Schrödinger equation and so on, which was my specialty at that time. So Zakharov and me in 1971, we calculated angle action variables for this Korteweg de Vries equation. It turns out that the action variable is a function of this reflection coefficient, here all explicit formula, and also eigenvalues are to be added to that. And then angle variables are argument of R, and some variables which you have to add, conjugate to this lambda. They are characteristics of discrete eigenfunctions. And then in terms of this variable, the observables like Hamiltonian or momentum can be written in a very natural way, that they are taking this rho times lambda or rho times lambda to the 2/3, and there is contribution of discrete spectrum. So this formula, as soon as I have written it, reminded me second quantization. The Hamiltonian in the second quantized form is written as omega of k times a star a. So rho is something like a star a. And here we have strange particles with dispersion law lambda to the power 3 seconds, yeah, and so on. So it's clear that indeed we have to quantize it somehow, and then we'll get a theory with several types of particles, original particles corresponding to continuous spectra, and then to each eigenvalue of lambda, another particle. So there is really possibility of going from this paradigm of field theory, one field, one particle. The only drawback was that equation was very non-relativistic. But anyhow, we have written an article which was called Korteweg de Vries equation is completely integrable Hamiltonian system, and I think that this new term integrable appeared out of that article. Well, in 70s there were a lot of development in this direction, about solitons. So examples of equations which have solitons on the continuous space, on discrete space, so nonlinear Schrödinger, Toda lattice, sine Gordon, and so on. Also, people considered not infinite axis, but finite interval with some boundary conditions, and then solutions are given in terms of the elliptic functions. A lot of even new theorems about elliptic functions were mentioned, were proved in this way. The most people in my vicinity, it's Sergei Novikov in Moscow, and Itz and Matveyev in St. Petersburg, in Leningrad, who were doing this finite. There appeared in particular some new thing for solid state physics. You know that when you have periodic potential, then spectrum is continuous, but with zones. And so solitons models were giving you examples where there was just finite number of zones. So finite zone solutions were quite beautifully interesting. But then, when in the late 71, I was first time in America, John Clowder told me, but why don't you try sine Gordon? There is this interesting equation. So this equation looks like, hyperbolic equation with nonlinearity written in terms of sine instead of phi. It's just linear thing. I think it's not very good taste to rhyme sine and Klein, in particular because the Klein was not author of Klein-Gordon equation. Klein was among them, Gordon was not, but, and it's kind of sine Gordon. So Gordon was not the author, it was Fock and Klein. Anyhow, but now this is a relativistic model. So solitons are really begin to be new particles. But very interesting that besides just stationary solutions of corresponding equations, there are also periodic solutions. And phase space of periodic solution, besides coordinate and momentum, had also some internal angles. And this part of phase space was compact. So when you quantize, you are to have finite number of states. And so quantization of these so-called breathers gave me a full spectrum of particles, very beautiful formula, which was lost in mail when we sent our paper to physics letters. And so it was published before us by Daschen, Haslacher, and Neuer. Another beautiful property of Sine-Gordon was that interaction of solitons was strong when you had weak, so coupling constant gamma is here. It turns, goes in here. And so for when gamma goes to 0, of course, you have Klein-Gordon equation. And so that's weak field is just this field which corresponds to this in usual field theory. And then other things have gamma in denominator. So besides weakly interacting fields, you have also strongly interacting particles. I was quite amazed with this. I advertised it in America in the middle 70s. I was speaking with in Harvard, in Princeton, and so with lectures and saying them, you know, there is possibility of having strong interaction in terms of weak interactions. There is some text about this, but things are, in fact, were quite more complicated. At that time, I was too enthusiastic. But anyhow, as soon as you have this relativistic problem, immediately you want to quantize it. When you have angle action variables, you can quantize semi-classically. So, for instance, those states of breathers, I say, quasi-classically, where could be found from this finite phase space of finite volume. But we wanted to have exact quantization. There were two reasons that one can get exact quantization. One of them was paper of mathematician you know, my age, I forget names. American person in the inverse problem. He have shown the so-called Toda model is connected with representations of SLR group. And so, you know, that representation theory is quantum mechanics of phase space corresponding to the group of so-called coadjoint orbits. And so, apparently, there were ways of thinking that there must be exact quantization. What's the name? No. Kirillov invented orbits, but American in MIT, let's see, not name with B. No, not. Maki is too old. No. Well, anyhow. And so there was clearly, it became clear to the middle of 70s that one can quantize exactly. And we began to do a lot of quasi-classical calculations, but then somehow abruptly there appeared a new idea which finally led to so-called algebraic Bethe Ansatz, namely which I developed with very group of people of my students. Students means that they have finished university under my, and then come to work with my group in the institute. So I mentioned Sklyanin, Karepin, Izergin, Kulish, Semenov, Sanshansky, Shetikhin. There are many others, yeah, but anyhow. And there was, so what I have here. And so I will now describe you the outcome of this thing, and then tell you about story how we come to that. So forget about all I said, and now let's consider very concrete problem from quantum mechanics, which is called Heisenberg spin 1/2 XXX chain. So dynamical variables are spin variables of representation, two-dimensional representation, the simplest. So here are commutation relations for different sides of my chain. They commute. So the Hilbert space for each spin is just two-dimensional complex place. So the full Hilbert space, if I have my periodic and then n plus 1 is equal, so it's just periodic. So the full Hilbert space will be tensor product of these two things, have dimension 2 to the n. And so spins, if I be more exact and say that spins act only on the place number n, and spin is on the nth and one afterwards, so they're now operators in this tensor product, then Hamiltonian looks like constant J times scalar product of two adjacent spins, and there is periodicity condition that Sn plus 1 is equal to S1. Well defined Hamiltonian just in the matrix dimension 2 to the n, but when n is big, then 2 to the n is also very big. So, and in fact, some things simplify when you go to the limit. I will describe you the answer somehow, and and then a little bit about technique. So this model is very instructive because it has all the features of field theory: the degenerate vacuum, the symmetry breaking, new particles, and so on. And the situation is very different for case when J is negative or J is positive. It's clear that the state when all spins turn in one direction is kind of is an eigenvalue of this operator. But spin can go up, can go down, can go some other directions. So you have a lot of vacua which are degenerate. And now if you choose one, which makes that you make symmetry breaking, for instance, if that all S3 goes up, then you have you have an eigenstate called a ground state. It has energy proportional to n. If you take now n equal to infinity, then operator S3, after you subtract maybe the value for on vacuum, has sense. But operator S plus and S minus, or S1 and S2, have no sense. They're now just broken. So the SU2 symmetry, which you had at the beginning, is just broken by this vacuum. So it's the simplest thing which you do with ferromagnets. You know it better than me. So it already appears here. And then excitations can be obtained by Bethe Ansatz, about which I will not say too much. But they are could have any value of S3 shifted by this big one. So there are a lot of just infinite number of different particles with a spin, which might be called with different value of S3, which are to be called magnons, and they are here. So there is a spin 1 excitations, magnon, and then there are many excitations of which are bound states. One can write down S matrix and so on, so everything can be done explicitly. But then antiferromagnet is completely different. Now the excitations above this vacuum, I did not say it in previous transparency, they are negative, the simple excitations. And so now you can speak about Dirac C of such things. Dirac C is allowed because it turns out that states are labeled by some parameters which can coincide. So that really excitations are Fermi-like. They are they're not fermions, but they are Fermi-like, namely that with one particular quantum number, one can have only one particle. So you can speak about Dirac sea. Very good. Turns out that vacuum is Dirac sea of such excitations. And then you can speak about excitations above that vacuum. And it turns out that those excitations have spin 1/2. So once more, all your SU2 group, which was there, is realized explicitly because excitations for given energy, there are 3 of them, and exactly corresponding to. So symmetry breaking is shifted, and you have very different. The construction of Dirac sea was done of course, the first person who will begin to discuss these excitations was Gans Bethe. He used what's called Bethe Ansatz. I maybe say some words about this later. But so it was paper of, I think, 1933, 31 even, yes. Yeah. And then Hulten, Swedish physicist, have done this Dirac sea. So he found true vacuum in 37. After that, there were a lot of papers about excitations, but unfortunately they were wrong. And then I was lucky with my colleague Leon Takhtajan to understood analyzing properly Bethe Ansatz, all those number of states, quantum numbers, and so on, that there are in this chain of odd number of states, excitations are vacuum, 2 particles, 4 particles, and so on. If your chain is odd, then there is no vacuum, there is 1 particle state, 3 particle state, and so on. Very strange situation, but anyhow it works explicitly, and so those excitations. So in a way, to cover full field theory, you need chain with odd end and even end. And so the corresponding particles, just one sort of particles, they're what are called spinons now. We didn't know this word, it was invented after us. Now, let me return to the beginning of my talk and to say how this spin chain, which already quantized somehow, is related to inverse scattering method. It turns out that all construction of observables can be done in terms of also analog of Schrödinger operator. You remember, we had the Schrödinger operator, second derivative potential, so things dependent on dynamical variables plus lambda, plus k squared. So here, my dynamical variables are spins, so I put it in matrix 2 by 2, plus and this minus, and have this also lambda, which is something like k squared. And consider now, with this matrix, that I have now the discrete analog of the differential equation. So I will multiply them. So index n will correspond to point on the chain, and I multiply them and so on. And then it turns out that the product of all of them is very important. But before doing it, I want to tell you about the commutation relations. You remember I told you that in Cartevec de Vries we were calculating what Poisson bracket delta prime looks in terms of angle election variables, or in terms of the scattering data. So here we have also simple Poisson bracket for S, you have seen them. And we want to recalculate them in terms of the objects which appear out of this chain. In case of Cartevec, I told you that we were to use a lot about scattering theories, for property of Schrödinger equation, and so on. But then now we realize that there is a way around this. There is a very natural way, algebraic way, to derive commutators of scattering data in terms of original commutators. And this is based on very important relation that if I take 2 ln for the same lattice site, but 2 of them, depending on parameter lambda and parameter mu, if they tensor multiply them, then the product in opposite direction is equivalent, is adjoint. There is a numerical matrix R such that these things are the same. Now, so how it was invented? It was invented by observation that the machinery which we do in inverse scattering method and machinery which people do in statistical mechanics, classical statistical mechanics on the plane are very much the same. Indeed, in statistical mechanics on the plane, you have a vertex which is called Boltzmann weight. So it's spin 1/2, it's the same. There are the same spaces, up and down. So so it depends on 4 indices. And then you construct so-called transfer matrix. Namely, that you multiply all Boltzmann weights along one line in your lattice, and then you get matrix, and then the full free energy with the product of this matrix is up. So somehow, in the purely classical mechanics, there appeared quantum mechanics in the sense that you have transfer matrix is a matrix. So something like quantum mechanical thing. And so it's and then people like Baxter have invented special sort of integrable of the exactly solvable statistical mechanics model for which the Boltzmann weights satisfy some trilinear equation. And this trilinear equation we have rewritten in terms that this auxiliary direction and quantum direction are different, so that, but in fact, in case when you have 2 by 2, well, Boltzmann weights with 2 by 2 matrices, R and L are matrices of the same sort. So that rewriting Baxter in terms of some auxiliary and quantum matrices, we come back to inverse scattering problem. And indeed, this is satisfied. This is, of course, can be rewritten in terms of this picture. But then, very beautiful, how to calculate now the analog of scattering matrix will be product of all this L along the line. It's just, you are solving your equation, which is kind of lattice analog of differential equation. And then out of the previous relation, it turns out that M satisfies just the same relation as L. You just multiply them and you find that the same relation is hold. So all stuff, calculating Poisson brackets of scattering data, somehow must be forgotten. Just this relation give you necessary commutation relations. Out of them, it follows that the trace of monodromy, is now a commute for different lambda. And so we can consider T of lambda as generating functions of conservation laws. For that, of course, you have to find out that Hamiltonian is among them. And calculation is shown that Hamiltonian can be considered as logarithmic derivative of T at point I over 2. And on the other hand, from the previous transparency, it's clear that monodromy is polynomial in lambda power n. The highest power is trivial, but then others have coefficients. So there are n minus 1 non-trivial coefficients, and together with h, they give you all action variables. So number of conservation laws is here. So we were very proud that completely different directions, statistical mechanics, classical statistical mechanics on the plane, and inverse scattering method for Korteweg are coming on the same footing. The difference, of course, is that for the case of Korteweg, our L operators will be different from our matrix because they are, so dimensions of the auxiliary space and quantum space could be different. Then one can begin doing different auxiliary spaces. Well, now as soon as this was understood, there was immediately field of work for many people and for many results, which indeed followed. So some generalization I will mention. One of them is to take higher spin. So Heisenberg, analog of Heisenberg Hamiltonian clearly is not integrable, it's known. But if there is something, yes, so it was to be understood that now, how to say it, this monodromy is not convenient for defining the local conservation laws. Because in doing local conservation laws, it was very important that R of lambda for lambda equals 0 was permutation. So and if you have higher spin, then R will be not symmetric. It will have still 2 by 2 for auxiliary space and 2s plus 1 for spin space. So it cannot be permutation. So one was to invent another Lux operators, another spin, Boltzmann weights, which were also matrices S by S. 2s plus 1 by 2s plus 1. This comes out of some beautiful machinery, which was formalized by Skliani, Revshitich, and Kurish. And there you were able to get Hamiltonian for any spin, which was integrable. In the case of spin 1, for instance, it's not quadratic. It has terms, of course, of Heisenberg spin, but there are also added some quadratic 4-order combinations in spins, and then this Hamiltonian is also exactly soluble. It's very beautiful Hamiltonian because, well, in particular, when you take spin equal to infinity, you are to get something like nonlinear sigma model, and I have some indication about that, but not completely. Also, there was a paper of Affleck where nonlinear sigma model was somehow connected with infinite spin Heisenberg chain. And we have an unpublished paper with Dr. Jan about that, but there are a lot of connections in this case. So that's about XXX. A lot of things can be done. Well, one of them will be later. Yeah. So then you can consider more complicated Hamiltonian. In case of spin 1/2, it's called anisotropic XYZ model. So you have different coefficients in front of the scalar product of spins, J1, J2, J3. There's partly symmetric case when J1 is equal to J2. It's called XXZ. For spin 1/2, you can write down corresponding Lux operators. Of course, the Boltzmann weight of Baxter model. But for higher spin, I will speak a little bit later. Now, until now, it was rank 1 SU2 group, essentially. So you can get in other groups, another spin type of variables, in other representations. So you have a lot of parameters in this. Now you can introduce, you can continue continuous limits. You have lattice spacing. Now I had lattice, but now I will say that I have delta distance in the lattice. Go to limit delta equals 0 and get a lot of continuous models. So nonlinear Schrödinger, Korteweg de Vries, all of this can be found from spin chains by appropriate limits. one can also consider inhomogeneous spin chains, namely changing parameter lambda in different points. The Young-Baxter still works. Integrability still works. You have also more parameters. It turns out that sine Gordon can be obtained by XXX chain with spin minus 1/2 and with some inhomogeneity, so you shift lambda in one direction and in the opposite direction on the next point and so on. So it's kind of this quenched chain and so on. So in a way, spin chains happen to be quite universal models, out of which most of machinery of 70s, classical, quantum, and so on, can be obtained if you work hard enough. So I say here quite dear thing that all integrable models are different limits, and so the spin chains are universal. Well, but then there are a lot of new mathematics, namely that the fundamental commutation relations are LL. For XXZ model with higher spin, in the space when spin variables act in more complicated space, take place only when you change commutation relations of spin. So you have some homogeneity in XXX model, call it this parameter gamma. Essentially, J1 equals J2, and then J3 is kind of cos of gamma, something like that. So Kulish and Rishetikin have found that all machinery works only if the spins now have less trivial commutation relations. That S plus and Sn, S minus, not equal to S3. They're equal to what we call Q analog of F3. So sine divided by sine gamma F3 divided by sine of gamma. When gamma goes to 0, then you have F3. So when they have shown it, I looked and say, but so it's new algebra. Is it some cell consistent and so on? So we looked at it a little bit too long, and then Greenfield came and told us what we are doing is called Hopf algebra, and invented this term quantum groups. So we were a little bit behind, and so decided then to rewrite our approach to all these things. And there is a paper by Takhtajan, Rishetikin, and me, which is called Quantum Groups, which explains this arithmetic formalism of doing quantum groups. These fundamental commutation relations are LL, which I have written, in fact have a even more long history. So as I told you, it appears in Boltzmann-Waite in the classical statistical mechanics, beginning with Ansager, not in Ansager, but in Lieb and in Baxter. But also, this R can be considered, it has 4 legs, can be considered as scattering matrix. And that's a special scattering matrix, which for 3 particles is factorized. So there are examples when scattering, many particle scattering, can be factorized. So you need only 2 particles as matrix, and 3 particles matrix is just product of them somehow. So this factorized scattering was discussed by many people, also in my group, but I mentioned Felix Berezin, Young, Brezan Zizhusten, and so on. So it was to be called somehow. And now I must confess that we were to choose. So some people told me, well, Ludwig, if you did not call it, it will be your relation. But I decided no. I remember Poincaré, who called one more German guy. Well, anyhow, yeah. And so we were thinking which names to give, and decided finally to call it Young-Baxter. In fact, in our paper we written Baxter-Young to have alphabetic. And then I don't remember, somehow it was to change. Young always want to be first, so it was somehow. So in original paper, recently Young asked me, where did you introduce young Baxter? I say, in that paper, look at it, it was Baxter Young. Well, see, really. Well, anyhow, so it's now, so we dubbed all this machinery Young Baxter relation, which is now, is from time to time forgotten how it come from, but anyhow, it's my responsibility. Well, it's all very nice, but now about physics. Until now, all these problems were one-dimensional. The one-dimensional systems like quantum, like spin chains, have physical meaning, and there must be some application to quantum computers, I'm sure. There are certainly applications in quantum optics and so on, but nevertheless, it's still one-dimensional. So, in a way, it's a beautiful mathematical structure. Also, mathematics like quantum groups and so on appeared and so on. But nevertheless, some physicists could say, well, what you are doing with these one-dimensional things, not very impressive. And it was very interesting that in the end of previous century, beginning of this century, there appeared new signature of integrability in four-dimensional quantum field theory. There, there is a chain, but this chain does not correspond to space dimension. It corresponds somehow to labels of some operators and so on. So when you consider many operators, you have a label, and you can speak that you have chain. And then, in particular, the many particle scattering in Regge type by Lipatov has such chain which is artificial, but nevertheless he have written a very nice Hamiltonian, which completely unexpectedly happened to be Hamiltonian of XXX model of spin minus 1. So it's infinite dimensional and so on, but nevertheless it's exactly like that. I remember I was in Stony Brook, and some student, well, graduate student, Karchemsky, came from conference in Minnesota, and he told me, you know, Lipatov goes with your paper and says something. I say, but what is that? He said, there's such a Hamiltonian, extremely fancy Hamiltonian, written in terms of the momenta variables, logarithms of momenta, something. So I told him, if you can fit it into gamma function, which is our universal arithmetics, then I can understand what's going on. And Karchemsky have done it. And so we have a paper. So I was somehow, just first time I was author because I know something, not that I have done it, because I was able to say that I know it. So there is this paper of Karchemsky and me and Lipatov by himself, and where there is a spin minus 1/2. Then in the beginning of the century, Minahan and Zaremba began to do with n equal 4 super-Young-Mills theory, and have shown that some anomalous dimensions of operators there can also be found from Bethe Ansatz. So there is also spin chain somehow behind it. So the label of operator was just a point on the chain. So it's four-dimensional operators, even more than this. But now this apparently attracted a lot of people. So when I say you in the beginning that word integrability was mentioned many times, so that's because mostly of this activity. There are a lot of activity. Germans, Bayer, Schaundacher, Russian, Frolov, Rutsunov, who was here, Kazakov in France, so Russians abroad mostly, and many other names. So their results are now published in a special volume of Journal of Physics A, very thick volume with many results and so on. Then vacua in supersymmetrical topological field theory, associated with names of Nekrasov and Shatashvili. Shatashvili is from my group previously, yes. That's also was quite popular now. So. And many other examples. But I will finish with some strange comment that Feynman was interested in this. Sometime in the middle of 80s, I think, I got from World Scientific, you know, they send from time to time some releases. So a very short release where Feynman cited Feynman, and Feynman said, if I was able to find Bethe ansatz with more than 2 polarizations, I will do a lot for high energy physics. Apparently he was thinking about, in high energy physics, scattering is mostly, collision is mostly one-dimensional, and that polarizations are just degrees of freedom which describe these particles and so on. I say, of course, higher spin, XXX, more polarizations, clearly. But he just died. So, so there was no connection. So when I visited Pasadena a little bit later, I found on the blackboard, which was still not erased by John Schwartz, several cryptic words. To learn, double dot, and to learn turbulence, quantum Hall effect, and Bethe ansatz. I was very amazed. Yes.
Can I make a comment at this stage? Actually, Alexios Polykranakis, who was the...
I know, I will tell you.
He claims that... Okay.
No. Well, what I have seen on the blackboard was indeed written by very nice script. And that was apparently Polykranakis. But the photograph in physics, letters in physics today is completely different. So I was amazed when I found the photo in physics today. It was completely not the one which I have seen. But with Polykranakis, it was, of course, true that it was in a very nice script. And then I asked secretary, you know, Southern California secretary, there's Mr. Feynman, yeah, so on. What's left? And she brought me this thick pack of files in very nice script, and every page is date, hour, and so on. Apparently it was his. So, and then all our names were there, so I was so proud. But then I was to go, somebody told me we are to run, and so I did not take too much of that. But apparently, Polykranakis was just taken by Feynman to teach him, because, for instance, the way how to write down tensor product of two 2x2 matrices explicitly there. I was very, very glad to see it. Anyhow, so Feynman was also interested in it. So I think that as soon as people like Feynman are still interested in integrability, this is not bad. So it's really new life, and I tried to tell you in an hour what's going on. Thank you.
Questions? I'll start by making a quick comment. Maybe in the end it's been good for the mathematical physics of integrability that it wasn't publicly known that Feynman had an interest in it, because otherwise there would have been hordes of people.
So that's why I say here. So it's why not? I can tell you opposite. I think in middle of 80s, I had a lunch with David Gross, and he told me, now, Ludwig, finally, Ludwig, you are dead, because your integrability nobody is interested in, and you will never learn string theory. so I'm vindicated, I think.
I always wondered who invented the name for the R matrix, and why is it called the R matrix?
I think if I remember right, no, R is just letter, and I think it was written by Sklenin first.
No particular reason.
R for ski.
No, no, no. No, no. Quite modest person, yeah. Yes.
Well, I mean, people were talking about the classical R matrix beforehand, right?
Yeah.
So that's where the classical.
It's a mystery for it's always been mystery for me why it is an R matrix, not a Q matrix or an M matrix.
Well, Q is more busy. R is just neutral letter, not used too much. So.
I thought it was R.
Okay, my deeper question perhaps is, do you have any, well, you've got a lot of experience with integrable differential equations and integrable models in 1+1 dimensions. Do you have any explanation or perhaps any model of the answer why out of billions of equations that you can graph, there exist some plausible, physically reasonable equations which happen to be integrable? That's quite mysterious.
Well, it's our luck. I can't say really. No, there is no classification. There is no. I know that Shabbat tries to do some classification of integral models, but I think it's not interesting. So I say just the opposite. We make an atlas of integrable models, mainly spin chains, and then see where you go to the limits. But given an equation from the beginning, it's very difficult to judge.
Well, this may be a little bit far-fetched, but you, of course, here on this slide also you mentioned supersymmetry as one of the ingredients in construction.
Well, this is one of the examples that is used.
Right. No, very long ago there was a paper by you and Popov on ghost fields in gauge theory.
Yes.
And we know that there is also a symmetry structure behind that, the BRST symmetries.
Yes.
So is there also an example where this is related to integrability, this BRST symmetry?
No, for me not. I would say that BRST is just property of Young-Mills, which is not integrable, and somehow...
well, not just Young-Mills, right? Because if you have gravity or other theories which have gauge invariance...
Well, formally in gravity we have the same. We also have ghosts, but it's not normalizable, so what to do with
string
it?
theory.
Well, we'll see.
It's a little bit related to the previous question.
A little bit louder.
You mentioned all these applications where there is integrability.
Mm-hmm.
But is there anything generic that could make you suspect in advance that there was some integrability?
No, for me it's very...
specific application, you of course know why it works the way it works. But
Well, for me it's unexpected, and I think it's... you cannot, as I say, you cannot give some prediction there and there and there of the integrability. And in fact, in my mind, the quantum field theory in 4 dimensions is very different from integrable models.
Yeah.
Namely that, so I don't like n equal 4 because beta function is 0. I think that beta function non-zero is much more interesting. And so you have to have negative beta 1, and then you have dimension transmutation, and you have everything. And infinities are really good, not bad. That's what I'm trying to say to students. That Dirac, Feynman, all of them didn't like infinities, but in Young-Mills, infinities are good. They just break scalar invariance of Young-Mills, and quantum field theory is very different. It's not scalar invariant. There is mass parameter, not Higgs, just... but it's only scaled. So the Young-Mills theory is just one theory. It's no parameters at all. No weak coupling, no strong coupling. It's just numerical theory, so to say. And you have to get dimensions just to multiply by power of this parameter. That's it. I think that Wilczek somehow knows it, but it's still not in textbooks. I don't know why.
But 2 dimensions is usually preferred for this, right?
So in 2 dimensions...
And in this case you could say, well, there's something like string theory which is related to these examples, and that sort of gives you a different representation of the same physics. And perhaps that is the link that you have here.
No, what can say now that it's very good that there is a lot of signature of integrability in serious investigation of quantum field theory, but maybe it's in wrong field theory. Well, now it's sociological fact that now with so many young people educated in things, they know mathematics very well, they have to do something, and they try to find problems, and they call them field theory, but it's it's not the field theory which I think is important. It's not QCD.
No, it's close.
Yeah, just a remark. So many string theory know string theory. Of course, string theorists know string theory, but they usually can't talk to mathematicians because mathematicians don't understand their way of doing mathematics, so to speak. No,
I know a lot of mathematicians who know what is mirror symmetry and such things. No. Algebraic geometers are very much involved. And take somebody like Kontsevich, for instance, he knows a lot. And no, there are very good mathematicians who are interested in this. This is mostly calculation of numbers somehow. And quite beautiful calculations of numbers. But and they do it.
Kind of very nice question. By 60s, there were already several quantum models which we knew the exact set of wave functions.
Yes.
Lieb, Huub. Did it help for kind of understand the concept of integrability? It was, for me at least, like, I remember, young. So I've seen the papers which came from people who solved models, and I've seen how, like in parallel, somehow you solved first like classical Schrödinger equation, nonlinear Schrödinger equation, and then it went to quantum. Did Lieb solution help you, or it was somehow?
No, Lieb solution fits very well in the scheme, so no problem.
Was it kind of this? The model which Lieb solved, was it a suspect for kind of integrability when you see it?
I can tell you a story. I was visiting MIT, and Lieb was still there. And I gave a talk about Korteweg definition, so it was 71. I go, and he at that time was solving XXD model. He said, how interesting what you do. I told, how interesting what you do. We did not understand that it's the same thing. Exactly, that's happened here.
Okay, maybe if you have time, we can just simply thank our speaker again.
Is that it?
Thank you very much.